In this video, we're going to look at problems that would be on the college algebra portion of the AccuPlacer exam. So for this first example here, we're trying to solve this quadratic equation. So this is a semicolon saying that x equals. So that means we're trying to find what x is. So first thing when I look at this problem is I look at the answers and I see that there's radicals involved. So right away that's going to tell me that this isn't going to factor because these numbers are irrational at the end. So what I'm going to do is I'm going to use the quadratic formula to solve this. So in order to use the quadratic formula, the first thing we have to do is get this quadratic in standard form. So I start with 2x squared minus 5x equals 9, and I'm going to have to subtract over that 9 so that I get this quadratic in standard form. So then when I look at this value here is my a, this is my b, and this is my c. So I'm going to go ahead, I'm going to use a quadratic formula. So negative b plus or minus square root b squared minus 4ac all over 2a. So when we plug in for a, b, and c are just numbers. You don't do anything with the x's. So when I start to substitute in for b, it's going to be negative, and then b is going to be negative 5. So I'm going to plug in using parentheses. So negative 5 is what b is. A is going to be 2. And c, we're going to keep that negative, so it's going to be negative 9. All over 2a. All over 2 times a, which if you plug in for a, it's going to be 2. So then we go ahead and simplify this. So negative times a negative 5 is going to be a positive 5, plus or minus the square root of all of this. So this part here you could just put into a calculator, the part underneath the radical. So when you do that, you get 97, and then it's all over 4. So that's going to be choice D. So just make sure in the end too you're careful about when you're choosing your answer, because all of these are very similar. Especially pay attention to this negative here with the b, because you're plugging in a negative b and it's already negative. You have to remember to actually negate that or switch the sign. So that kind of can throw you off if you don't pay attention to that. The next problem here is a trig problem. So you're trying to find the exact value of cos of 120. So first thing you want to do is you want to figure out where does 120 degrees fall on our quadrants. So 120 degrees would be somewhere over here. So this is going to be my 120 degree angle. So that tells me that the reference angle, remember the reference angle is always measured off of the horizontal axis here, is going to be 60 degrees, because this whole entire thing would be 180. So 180 minus 120 gives me the 60 degrees. And then if you think about how we label our quadrants, all students take calculus. This tells us where the angles are positive. So in this second quadrant, sine is going to be the only positive trig function. So that means if I'm looking at cos of 120, 120 falls over here in the second quadrant, cosine's negative over here. So cos of 120 is equivalent to negative cos of my reference angle, which is 60 degrees. So then the last thing that I have to do here is I have to figure out what is cos of 60 degrees. So this is where the special right triangles are going to come into play. So if this is my 60 degree, 30 degree, and my 90 degree angle, the 2 goes across from the hypotenuse, that's the biggest. 1 is the smallest, so it goes across from the 30 degree angle, and radical 3 is in the middle of 1 and 2. So that's going to go across from the 60 degree angle. So if you're looking at cosine of 60, cosine is equal to adjacent over hypotenuse, the ka, so katoa, and that's the ka part. So if you're looking at 60 degrees, adjacent, so cos of 60 equals adjacent, which is 1, over the hypotenuse, which is 2. So then over here, it's going to be negative cosine of 60, which we just found cosine of 60 degrees is 1/2. So the answer to this question is going to be negative 1/2. The next example here is a log function. So for this one, again, it's giving you this log equation and then a semicolon x equals. What they're asking you to find is what x equals. So they're asking you to solve for x. So the rule for logs, when we go to solve them, log equations, we drop the log and we swing the base. So this is going to be x equals 64, and then it bumps this negative 2/3 up to an exponent. And if you remember, whenever you have a negative exponent, that's the same thing as doing 1 over that whole thing. And whenever we have fractions as exponents, those are roots. So the 3 is the root, and the 2 is going to be the power. So what I can do is rewrite this as x equals 1, and it's going to be the cube root of 64, and then it's all squared. The power is 2. So x equals 1. If you take the cube root of 64, so what times what times what gives me 64, is going to give me 4. I'm going to keep this squared. So 1 over 4 squared is 16. So the answer for this is choice A. And with logs, you always want to make sure that you check this and that it doesn't create 0 or negative, or taking log of 0 or negative. So the fact that we get a number 1 over 16 and we plug it in for x, it doesn't create 0, taking a log of 0 or negative. It's all good. And that answer checks and it works. The next example here is coming up with the equation of a line. So if you ever want to come up with the equation of a line, you're looking for y equals mx plus b. So you need to know the slope, and you need to know the y-intercept, or where it starts. So the y-intercept is where it crosses the y-axis. So here's my x, here's my y-axis. So the y value here, the y-intercept, is going to be 4. And then to figure out the slope, you do rise over run. Always start at the leftmost point and figure out how much did you have to go up or down and then to the right. So I had to go down 1, 2, 3, 4 and over 2. So the slope, I went down 4 and then over 2. So down 4 over 2. Since I went down, that tells me it's going to be a negative 4 over 2, which when you simplify gives you negative 2. So if you go to plug those things in, the y-intercept and the slope is negative 2x, and then the y-intercept is positive 4. So that would be choice E. The next one here is using our properties for exponents. So when we're looking at properties for exponents, you have to, in order to be able to do anything with the exponents, you have to have like bases. And in order to be able to combine any of these when you're adding or subtracting, you have to have the entire same term. So basically, in order to be able to combine any of these, I would have to have exactly the same base and the same exponent. In order to be able to do anything with the exponents, when you're adding or when you're multiplying or dividing, you got to have the same base. So for this one, the first thing I notice is that these are exactly the same. So instead of having two separate ones, what I can say is I have 3 to the 8/3 and minus, if I do one of these minus another one, now I have negative 2 of them. So basically I have negative 2 times 3 raised to the 5/3. So kind of think of it like an x. If you had minus x, you'd have minus 2x. So these kind of stick together. We can't really do much with them other than subtract their coefficients. So the coefficients of these are 1. So now, if I want to actually combine these, what I need to do is I need to rewrite this term here so that it's the same as 3 raised to the 5/3. So if you think about your exponent rules, if you multiply two like bases, you add the exponents. So what that allows me to do is it allows me to rewrite this expression here as a product of 3 raised to some power times 3 raised to some other power. And I want to make one of my exponents 5/3. The reason why I want to make one of my exponents 5/3 is because right here I have 3 raised to the 5/3. So now I have 3 raised to the 5/3 right here. So what I need to do is I need to rewrite 3 to the 8/3 as a product of 3 raised to something times 3 raised to the 5/3. So the rule for exponents, remember when you're multiplying like bases, is you add the exponents. So when we add the exponents, I need to be able to get 8/3. So that tells me the denominator has to be 3, and the numerator would have to be 3, because when you add fractions, you add across the top. So 3 plus 5 gives me 8, and the 3's on the bottom just stay, because adding fractions, you keep the denominators, you actually add the numerators. So this expression right here is equivalent to this, because we're multiplying like bases. You add the exponents. If you add the exponents, you get 8 to the, or raised to the 8/3. So then I'm just going to carry down this other piece. So then from there, instead of having this 3 raised to the 3/3, I'm just going to change that to 3 to the 1. So then I'm just going to rewrite everything else. 3 raised to the 1 is just 3. So now this seems a little bit weird, but basically we have like terms again. So think of it this way. If I had 3x minus 2x, we would get x, right? We would have 3 minus 2 and get 1, and we just kind of carry along the x's. So almost think of this expression here as an x. So I have 3 of them, and then I take away 2 of them. That tells me that I'm going to be left with 1 of them. So that means I'm going to be left with 1 of these. So my answer, 1 times this, is just going to be 3 raised to the 5/3. So that would be our final answer here. So choice B. The next one here, you're given a quadratic and they ask you to find, what does this quantity equal? What does x minus 7/10 quantity squared equal? So as soon as you see this notation here where you have a whole quantity being squared, you want to be thinking about completing the square. That'll actually get you right to the answer. So complete the square is the process that we're going to use. Now, if you forgot about completing the square, you could solve this equation for x. Just plug x in, x minus 7/10, square it, and whatever you get is the answer to the question as well. So you could do it that way, but completing the square would definitely be the shorter way of going about this. So I'm going to start with my quadratic for completing the square. First thing you always do for completing the square is you move the number over. So you don't actually want it in standard form. You always want the x's on one side and then the numbers on the other. So I bring that 6 over. And in order to be able to complete the square, we always have to have a leading coefficient of 1. So what we're going to do is we're going to divide everything by 5. Even though it doesn't divide nicely, we're still going to divide everything by 5 because you have to have a leading coefficient of 1. So basically what that tells me is I'm going to leave things as fractions here. So we're just going to leave all that stuff. So now I'm at the stage where I can complete the square. So I'm going to draw out the square. And we're trying to figure out what number would I add to both sides to be able to complete this square and make it a perfect square. So basically a quantity squared. So we always split this up, so x and x. And then to get what goes on the sides here, we always take half of this b value. So we're going to take negative 7/5 and we're going to divide that by 2. When we divide that by 2, you're going to get negative 7/10. So that tells me negative 7/10 goes here. And then when you multiply those, that'll tell you what number you're adding to both sides. So negative 7 times negative 7, positive 49, 10 times 10 is 100. So that means we'd be adding 49/100 to both sides. So then what we end up with on the left-hand side here is x minus 7/10 squared, quantity squared, because those are the sides of the square. Those are also the, when you take half of the b value, that's how we get this. And then on the right right-hand side, we have 6 over 5 plus 49 over 100. And you could just put that in your calculator and then do math fraction, and you're going to get 169 over 100. So it's asking me, what does this quantity equal? Well, it equals 169 over 100. So that's much quicker than if you actually solve for x using like the quadratic formula and then plugging it back in. The next example here is talking about the cost of pears and apples. So 3 pears and 4 apples cost $3.55. 5 pears and 3 apples cost $3.90. 1 pear in cents cost. So first thing I'm going to do is I'm going to write some let statements. I'm going to let x equal the cost of pears and y equal the cost of apples. And basically, I see two equations here. So that tells me I'm going to have a system. So the first thing is 3x's plus 4y's is going to equal $3.55 because 3 pears times the cost of each pair, so 3x, plus 4 apples times the cost per apple is going to equal the total cost of those items, which is $3.55. And then the same thing for this other one. 5 pears times the cost of pears plus 3 apples times the cost of apples is going to equal $3.90. So then from here, you have a system of equations and you need to solve it. So you can do it two ways. You can solve it by using substitution or you can solve it using elimination. It's up to you how you want to go about doing it. I do recommend though that in the end, you're trying to find what x equals. So if you're going to do elimination, you should eliminate the y's so that when you solve your equation, you get your x value and you don't have to plug it back in. If you're going to do substitution, you should solve for y so that you can plug in and replace the other y so that, again, you save a step. You don't have to solve for both variables. It doesn't matter if you solve for both variables, but just to save yourself some time, you could just solve directly for x. So I'm going to use elimination, which means I need to be able to eliminate, let's say, y here. So I look at 4 and 3 and I have to figure out a number that they both go into so that when I multiply the equations by some number, I get numbers that are going to cancel. So 3 and 4 both go into 12. So that means I want one of them to equal positive 12 and the other one to equal negative 12 so that when I add these, they cancel out. So I'm going to just make the top one equal positive 12. So I'm going to multiply everything by 3. And then on the bottom, I'm going to multiply everything by negative 4 because I want to make this become a negative 12y. So over here, we're going to have 9x when we distribute our 3 plus 12y equals $10 and so then for the next one here, we're going to multiply by negative 4. So we're going to distribute negative 4 through. So you're going to get negative 20 minus 12y. And then negative 4 times $3.90 is going to give you negative 1560. So then what happens is you're going to add these up. So when you do that, you're going to get negative 11x. The y's are going to cancel. And then you're going to get negative 495 here. Divide both sides by negative 11. So when you do that, you'll get 0.45, which is telling us that pears are going to cost $0.45. So 45 cents is the cost for pears. So choice A. The next one here, we're looking at our trig identities. So the first thing is this expression right here comes from 1 plus cotan squared is equal to cosecant squared. So if I rearrange this, meaning I subtract cotan from both sides, I'll be left with a 1 equals cosecant squared minus cotan squared of x. So I basically just subtracted the cotan. So if you look, that right there is equal to this. So that tells me that that's really equal to 1. So now I'm left with 1 minus sine squared of x. So the next identity, whenever we have sine squared, is your Pythagorean identity. So we have sine squared x plus cosine squared x is equal to 1. So if I subtract sine from both sides, I'll be left with cosine squared of x is equal to 1 minus sine squared x. So instead of 1 minus sine x, that's equal to cosine squared x. So just kind of using the different identities to simplify this, you get choice A. The next one here, again, we're asked to solve for x because it gives you this equation, then it says x equals. So the first thing you want to do for this is get this equal to 0, because if you look at your answers, they're all either integers. So that tells me that we can factor this. So before we can factor that, we have to bring that 4 over. So if we subtract 4 from both sides, it's going to give me 6 and then equals 0. So I just subtract 4. Then you're looking for numbers that add to -7, multiply to 6. So we have two sets of parentheses equals 0, x and x. We're multiplying to a positive, so that means I have to have the same sign. And since I'm adding to a negative, that tells me that both numbers have to be negative. So the only numbers that are going to multiply to 6 are 2 and 3 and 6 and 1. And in order to be able to add to -7, we would have to use 6 and 1. So then you split each piece, set this equal to 0. So then you subtract or add the 6 over, so we get x equals 6. Add the 1 over, we get x equals 1. So our answer's 6 and 1. Next one here, we have a log equation, so we're trying to find what x equals again. So we're trying to solve this log equation. So the first thing is to remember our log properties. So whenever you have a log equation, if you're subtracting, that really means that you're dividing the pieces that you're taking the log of. If you're multiplying, or if you're adding, that means you're multiplying these. So the fact that it's subtraction means that I can rewrite this as log base 3 of x divided by x minus 3. So it's going to be x over x minus 3. And that's because it's subtraction. If it were addition, then I'd be multiplying those. Then I keep the equals 3 on the right. So now we're trying to find what x equals. Now what we can do is we can drop the log and swing the base. So we have x over x minus 3 equals 3 raised to the 3. So x over x minus 3 equals 3 raised to the 3 is 27. So you can put that 27 over 1, and then we can just cross multiply here. So we have x equals 27 times x minus 3. Make sure you put x minus 3 in parentheses because it's a whole quantity, or it's a binomial, so you got to make sure that you distribute. So now we have x equals 27x minus 81. And then get x by itself. So subtract 27 from both sides. So we get negative 26x equals negative 81. Divide everything by negative 26. So we get x equals negative over negative is positive, so 81 over 26. And with these log equations, remember, you got to remember to check your answers. So if I were to plug this back in, it's not going to create a taking log of 0 or a negative number. So that means it is an answer. It does check. So the next page here, we have some rational expressions to work with. So rational expressions are fractions. So if you're trying to simplify something that has a radical in it, what you can do is you can rationalize. And in order to do that, you multiply by the conjugate. So the conjugate is whatever is in the denominator here, but instead of a plus, I'm going to do the opposite sign. So that means I'm going to multiply the top and bottom by its conjugate, which is whatever I have down here, but with the minus sign. So now I'm going to go ahead and I'm going to distribute this. So this becomes, I'm multiplying. So this times that. So if you have a radical x times a radical x, the radicals are going to cancel and it's just going to be x because it becomes square root of x squared. Square root of x squared is just x. And then the other one though, since they're not the same number, it's just going to become the square root of x times y. And then in the denominator here, if you were to FOIL all this out, you're only really going to be multiplying the first and the last terms because the middle terms will cancel. Because if you do a radical x times a radical y, you get square root of xy. Then if you multiply these, you get square root of xy again, but it's a minus, so the middle terms cancel. That's the whole purpose of this conjugate, multiply by the conjugate. So now what I'm going to do is I'm going to multiply these. So radical x times a radical x is just an x. And then I'm going to skip right to the outside terms. A radical y times a radical, or times a negative radical y is just going to be a minus y. So remember, I skipped showing the middle terms because they cancel, but you really should know that you do need to multiply those. The middle terms will cancel though whenever you're using the conjugate. So as long as you're multiplying by the conjugate, you don't need to worry about them. So this is as simple as we can go with this one. So your answer is just going to be choice C. The next one here, we're adding fractions. So in order to add fractions, you got to have a common denominator. So these two denominators don't have anything in common right now. So that tells me my LCM is going to just be the product of the two. So I'm going to go ahead and multiply this top and bottom of this fraction by 6x plus 7 so that I can get my common denominator. And then on the other side here, I'm going to have to multiply this one by x plus 4 so that I can get my common denominator. So my common denominator is going to be x plus 4 times 6x plus 7. And then on top here, when I go to distribute this through, I'm going to have 18x plus 21. And then for the other fraction, I have my common denominator, x plus 4 times 6x plus 7. Distribute the 5 through, so you get 5x plus 20. And then from here, you can rewrite this with one denominator. And then you add the top. So we have 18x plus 21 plus 5x plus 20. And then now we can combine our like terms. So 18x plus 5x is going to be 23x. 21 plus 20 is going to be 41. And then we keep our denominator. So our answer for this one will be choice D, because we can't factor anything or simplify it any further. Number 13 is just a calculator question. So sine inverse of negative 1/2. It's asking you what angle do you take sine of so that you get out negative 1/2. You can just put it right into your calculator. Just make sure your calculator is in degree mode since you're trying to get out degrees. And if you put it in your calculator, you'll get out negative 30. So sine of negative 30 degrees gives us out negative 1/2. That's what it's asking. And then the last page that we're going to look at for this video deals with compositions of functions, another log function, and then some inverse functions. So first thing here is compositions of functions. That's what this means. It means g of f of x. So we're going to input the function f of x into g. So first thing I'm going to do is just rewrite this as f of x is going to become the input into function g. So I just replace f of x with its equation. And now what I'm going to do is take this whole thing, I'm going to input it into function g. So function g, if you look at it, is 3 times x plus 4. So I just copy that down, and then instead of x, I put parentheses. I'm going to replace what I have in parentheses. And now we just have to simplify. So we're going to distribute. So we have 6x plus 15 plus 4. So we get 6x plus 19. So choice C. And you always are going to take the inside and plug it in to the other function. So just make sure it's g of f of x. So f of x is going into function g. The next one here is using log properties. So the first thing is we're trying to figure out what this is. So the first thing that I would recommend doing is rewriting this and setting it equal to x, because we're trying to basically figure out what this is equal to. So I'm just going to set it equal to an x. So this is 4 raised to the 3 log base 4 of 5. I'm trying to figure out what that equals. So I'm just going to let that equal x. And then what I'm going to do is I'm going to switch this into log form. If you remember, switching between log and exponential form, what you do, so if it's in exponential form, meaning b some base raised to some power equaling x, if I want to switch that into log form, it becomes log base, whatever the base is, of the exponent, or of x, is equal to the exponent. Because remember, logs are really asking you what power do I have to raise this base to get x. So when I'm looking at it, log base b of x equals a is asking you what exponent do you raise b to get x. So you would raise b to the a power to get x. So logs are always equal to the exponents. So this is your translating between log and exponential form. Going from log form to exponential, you just drop the log and you swing the base, and that'll get us to exponential. But going from exponential to log, you have to think about what's the base, becomes the base of the log, and logs mean exponents. So the log of that base of this number is equal to the exponent. So I'm going to use that, and I'm going to translate this into this form here. So it's already in exponent form. So the base is 4. My exponent is this entire thing equals x. So it's going to become log of b, or log base b, so b is my base, of x equals the whole exponent. So the whole exponent here. So 3 times log base 4 of 5. And remember, whenever we have exponents or coefficients, they can become exponents. So either vice versa, they go either way. So I have log base 4, if I just carry this down, of x equals log base 4 of 5 to the third. So coefficients are exponents or vice versa. So now if you look, we have log base 4 on both sides. So those cancel, and we're left with x equals 5 to the third. So x equals 5 to the third, well, x equals 125. If you raise 5 to the third, you get 125. The next one here, number 16, we're looking at this expression here. First thing we want to do is we want to get this so that we don't have any negative exponents. So if I have x to the negative 2 minus y to the negative 2 over x to the negative 1 minus y to the negative 1, first thing I'm going to do is rewrite this so that I have positive exponents. So this is the same thing as saying 1 over x squared minus 1 over y squared over 1 over x minus 1 over y. So this is what we call a complex fraction because there's two sets of fractions in one big fraction. So what I'm going to do is I want to find the LCM of each denominator, and then I'm going to multiply each piece by that denominator. So the LCM, the smallest number that all of these denominators multiply to, are going to be x squared times y squared. So that means I'm going to multiply each piece by x squared times y squared. X squared times y squared. And you can do this because we're multiplying the top and the bottom of the fraction by x squared times y squared over x squared times y squared. So basically we're not changing it, we're multiplying by 1 because we're multiplying the top and the bottom by the same thing. So now what happens is we just cancel some things out. So here the x squareds are going to cancel. If you multiply y squared times 1, you're going to be left with y squared. Here the y squareds are going to cancel, so you'll be left with x squared. In the denominator here, you're going to have one of those x's is going to cancel one of those. So you're going to be left with x times y squared minus, and then one of the y's will cancel. X squared times y. And then if you go to factor this, the numerator here is a difference of perfect squares, so that's going to factor as y minus x, y plus x. Difference of perfect squares, opposite signs, square root each piece. And then on the bottom, we can factor out a GCF of xy, because each piece has at least an xy in it. So we're left with a y. And then if you factor out an xy out of this, you're left with just an x. So that cancels those, and I'm left with y plus x over xy, which is the same thing as choice C. X plus y or y plus x is the same thing. And then the last question we're going to look at is this inverse function. So if it says find f to the -1 of x, that's the inverse function. So first thing you do, instead of having f of x, I'm going to replace it with a y. So y equals 3x minus 5 is the original, and we're finding the inverse. So set it equal to y. Second step, switch x and y. So it's going to be x equals 3y minus 5. Third step is to solve for y. So we're going to bring the 5 over. We get x plus 5 equals 3y. Divide everything by 3. So we get x plus 5 over 3 is equal to y. Well, it asks us to find f inverse of x. So f inverse of x is equal to x plus 5 over 3. So I just replaced the y with the inverse notation. Since this is a line, it is a function. So x plus 5 over 3. So choice C.